that, but also that's my, oh, I missed my first alarm. Oh, alarm.
Good morning and welcome to EORI Insights. We're pleased to have you. We're glad you're here in person and on the Zoom this morning. I'm Lon Whitman. I'm the director of the Enhanced Oil Recovery Institute. EORI has been working to develop a platform how we could bring information to the public on a regular series of presentations and information sessions to discuss with you areas of focus at EORI and developing world in the conventional sector of the oil and gas business. We received several suggestions that we tried this before work format, and we'll see how it goes. Thanks again for joining us. Our mission at EORI remains the same, assisting Wyoming operators to increase production in Wyoming fields and to minimize stranded oil in the state of Wyoming. Today's talk focuses on one reservoir in Wyoming that's complicated, perhaps for some mysterious, and we know has seen limited success in secondary or tertiary recovery, the Muddy Formation. It is a significant reservoir with significant upside potential if some of the questions surrounding this reservoir could be answered. We've done significant work at EORI already on the geology of the Muddy Formation. Today, Steve Whitaker, senior geologist with EORI, will present some initial findings and discuss with you challenges that he's faced in unlocking this important reservoir. Steve, many of you know, is a highly experienced geologist who's worked with both major and independent oil companies and has had his own company in the past. His work has included areas of mapping subsurface and surface geology, detailed prospect generation in clastic, carbonate, and unconventional reservoirs, working in petroleum engineering, geophysics, computer-enhanced mapping, reservoir characterization, development geology, optimization of water floods, IOR and EOR program design and implementation. We hope you'll find Steve's work on the Muddy interesting, intriguing, and helpful. And again, thanks for joining us.
Well, this is going to be kind of a nice informal discussion on some of the challenges as Lon was referring to on the Muddy. This is all stemming from work I started doing on the Kitty Field. I've done other studies too, and I'm trying to tie them all in together. So it's raising lots of questions and interesting points here. So the keyboard's not responding, however. So I think I'll start with this quote that I like from Park Dickey from way back in 1958, which is, "We usually find oil in a new place with an old idea. Sometimes also we find oil in an old place with a new idea. But we seldom find much oil in an old place with an old idea. Several times in the past, we have thought that we're running out of oil, whereas actually we were only running out of ideas." Wyoming is an old place, and the Muddy is a relatively old play. So we really need to be thinking of some new ways of looking at it in order to unlock, I think, some of the oil that was stranded there, and perhaps even improve exploration into that formation. So we'll start with the Muddy Formation as we think we know it anyway. And for those few people who maybe don't know much about the Cretaceous in Wyoming, in the early Cretaceous time, the subduction of the Farallon Plate, which was basically the Eastern Pacific back then, was subducting under the western part of North America, and that created a sag, a long linear sag over here, which started to infill with the sea. And through time, the seaway kind of had several pulses of rises and lows, still stands and retreats. And each still stand or retreat allowed sands to advance into the seaway. And one of these retreats resulted in the deposition of the Muddy. And these maps, which are by Ron Blakey, again, are really cool, but they're also based on geology as we think we know it. So lots of details within these maps are missing because we don't know a lot of the details yet. And part of what we're going to talk about here is maybe we've missed some of the detail in the muddy. The muddy was ultimately capped as the sea deepened into the Maori Formation, which is a great source rock and part of the, actually the main source for the petroleum system, which is responsible for the oil in the muddy. So let's jump in now to where the muddy is in our stratigraphic column. It's in the uppermost part of what we call the lower Cretaceous. And at the right, you see what's been an accepted model for the muddy deposition probably since the 1980s. This is from a publication I found recently in 2014. They keep modifying it slightly, but basically it's the same example. Sometimes people put an unconformity at the top of Skull Creek below the rosette. This particular one has the unconformity on top of the rosette. So here they'd say there's no unconformable contact going from the Skull Creek into the rosette. We'll talk about more about that a little bit later. But this big unconformity then eventually cut down into the Skull Creek, and the channels were then backfilled with what would be a fluvial sand in the Recluse, what's considered to be an estuarine sand in the Cyclone, and a shallow marine sand, the Ute, slightly deeper marine sand, and finally capped by the Marine Shell Creek, which is many people think is the bottommost member of the Maori. This particular paper actually has the topmost member of the muddy. Most people put the top of the muddy here in the Spring and Ranch. And as you see maybe later, there may be some method to their madness in this particular publication. So the muddy formation has produced over 300 million barrels in Wyoming. It's a significant reservoir. Almost all these traps are stratigraphic. Several of the fields in the muddy are still on primary production, even though they're found back in the 1960s. And this is mostly due to incompatibility with injection water from the Fox Hills Formation, which is where they usually get the injection fluids. Significant oil reserves remain in many of these muddy fields, therefore. We think there's at least 100 million barrels of recoverable oil left in existing fields, so it's a significant target. As an example, Kitty Field, which has made over 23 million barrels, at best has a recovery factor of less than 15%. So a lot of oil left there just in that one field. And because of this, many of the wells in the muddy are idle right now. And so we're actually having to lose some of them because regulations are forcing operators to plug out a lot of these wells. So we're losing access to recoverable reserves. So there's a time element on figuring out the muddy, because as we lose these boreholes, it's very expensive to replace them, and it's quite likely we won't replace them. So we're losing all these reserves. So it really behooves us to try and get after this as quickly as we can. Another point, many water floods in the muddy perform worse than expected when they can get a water flood going. Even those water floods don't perform as well as they had predicted. And it's pretty clear, I think, that improved understanding of the muddy and Newcastle Formation will result in production of additional hydrocarbons, which is, of course, what we're interested in. So this is a map based on tops from Geodigital, which is just one of the databases we have available to us. And this map suggests that the deposition of the muddy is at least partially controlled by an incised channel system. Most geologists feel that the flow in these channels was from east to west. Kitty Field's outlined there, which is was the focus of the beginning of this project anyway. And let's see, jump to this one. So we've got some questions that we'll start right away with. And this is based on ongoing work at Kitty, but expanded beyond Kitty. So first question is there a relationship between the underlying, like 1,000 feet below us, Permian Pine Hervé salt section and the deposition of the Cretaceous Muddy Formation? So again, this is where the Kitty Field is. Now, if you look at, whether the salt might be controlling some of that, let's look at this isopac map, assuming this thing rolls in here. Let's pretend it works right. There we go. So the pink areas are where the pine salt is preserved. The blank areas are where it has been dissolved away. Notice how many of the muddy fields are right on the edges of that salt front, or are where the salt has been dissolved. So it seems that there's a relationship here between the dissolving of the salt and the creation of muddy reservoirs. Now, this map is from 1981. It was presented in a paper in WGA in 1984 again, which is what this was taken from. But we need to upgrade this map because obviously there have been a lot of wells drilled since this time, but also they didn't use every well when they made this map. But it's a really good indicator that there's some relationship here, and it has really been ignored. In the 80s, we were paying a lot of attention to this, but after the crash in 85, 86, the baton for this type of study just really never got picked up. So I'm kind of intrigued to see if we could do that. And so as far as upgrading the map goes, if we can, this area here in the blue circle is an area where I had studied for a Menalusa study, but it also provides an example in the next two slides of some of the detail that we need to include in this type of a map regarding the thickness of this pine salt, Hervé salt. So here's a cross section. See just a few wells coming down through here near Little Mitchell Creek. And you can see the thickness of pine salt in a very short distance just disappears. If you look at an isochore of that, you see it looks something like this. And so there is quite a variance in thickness, and this thickness affects all the strata above it. When the salt was collapsing, everything above it was being dropped into this, dissolution graben, as it were. And a lot of that especially would be affecting the reservoirs that are being deposited at the time of the dissolution. And just as an interesting point, this field here is a one well field, rule field, Menalusa. This one well has made 1.5 million barrels of oil, even though it's surrounded by dry holes, only has one injector. That's going to be a plug for a discussion on the Menalusa I hope to have in this same series a little bit later this year. But the point here also is that the dissolution of the salt is going to affect seismic data, which is a factor in the Menalusa exploration, but also it is interesting where this dissolution is, that there's some muddy production right in this area. So, and there are actually shows in the muddy in these wells. So again, it's having an effect, I think, pretty clearly. So as far as Kitty goes, does this dissolution affect correlations at Kitty Field? Which is where all this nonsense started. So we'll look at this cross-section here, east-west cross-section going across Kitty to start with. And if you hang it on the top of the muddy, which is a typical datum people use when they're mapping the muddy, you can see a pretty clear indication that there is incision down into the underlying Skull Creek here, and you have a valley in the muddy. So what typically happens is then we correlate using that model and just draw lines across where the shale markers are, and we put the recluse and the cyclone and the Ute and the upper Ute and the Spring and Ranch and the Shell Creek shale up there like that. But are the correlations really this simple? The correlated sands commonly do not communicate as predicted. And cumulative production numbers commonly do not tend to align with predictions based on the volumetrics using those correlations. And the water floods in many of the muddy fields, when you initiate them, commonly underperform. So that's a clue that perhaps our correlations aren't as good as they ought to be. Now, I noticed in this particular well to start with, but all the wells, that there are some underlying marker beds in the Skull Creek Formation that may be used to be correlated. So if we look at that with great imagination, I label these things Skull Creek 1, 2, 3, 4, 5, 6, etc. going up. Dakota silts down here, but you can follow these beds all over this area. So using those beds as correlation lines, we now look at the correlation, and hard to see on this particular screen, but if you are at home, hopefully you have better resolution. You notice how these correlations follow the unconformity line. Well, that is not what you expect if you're having incision. In fact, if you flatten it on this, what I'm calling Skull Creek 7, you don't see any incision. This thing is conformable. This line here marked an unconformity is probably not an unconformity. And the rosette, which lies above it, and we'll talk about in a little bit, is possibly just a regressive sand continuation of the Skull Creek deposition. But you look at this, where's my incision? So perhaps this model is wrong. We need to rethink this. So I reduced a couple of wells off that cross section just so we can see the logs a little bit bigger. So these are the wells used in the following section here, just to show the train of thinking here as we correlate this, which changes how we correlate in Kitty Field. So here, again, hung on the same Skull Creek 7 marker, this is the rosette. And the rosette deposit is sub-parallel to the Skull Creek beds. There isn't a lot of variation there. And the rosette could, in fact, as I said, be a regressive sandstone continuation of the Skull Creek deposition that was forming as this Skull Creek Sea was receding out of the basin. So the rosette is known to contain much kaolinite clay, a common byproduct of degraded minerals, including smectites, volcanic rock and stuff. and is normally related to meteoric water influx, which suggests that the rosette was exposed to subaerial conditions. So it's a pretty strong case that this was, again, exposed to erosion. Now, if you map in the recluse, it can also be interpreted to be deposited roughly parallel to Skull Creek here. And you notice also how the sand exactly fills the supposed valley here. Now, this deposit could be explained as, well, yeah, we have an unconformity here, and it's incised into the rosette and just didn't really cut down into Skull Creek. And so that is still similar to what the model is, and that's fine. And that is not impossible. But how many times do you see a valley that is completely filled the bank full with sand? So it's just something to think about. Don't have an answer to that yet, but it is curious. And the sands within this channel could be from reworked rosette sands, which again would explain why the recluse sands have swelling clays in them and cannot be flooded with fresh water. An alternative interpretation for the recluse at Kitty anyway, is that perhaps it is nothing but a facies of the rosette that was deposited down dip from the coastal plain setting and is exposed to wave action that was winnowing out some of the clays, but not all of them, again, because it's basically rosette being cleaned up. And the rosette to the east of this is then just the down dip, more silty, shaly equivalent of that. And we're just looking at a facies change across there. Just something to think about. Now, if you start looking at the cyclone deposit, well, this clearly does not have bedding that appears to be parallel to the Skull Creek. So something has happened to the substrate here, and I'm postulating it's because of dissolution of the pine salt underneath this. If you flatten it on top of the cyclone, it looks like this. And the beds within the cyclone are pretty subparallel to that top of the cyclone and are not parallel to the Skull Creek anymore. And you do the same thing looking up the Ute. Again, that is not parallel bedding to the cyclone. You look at this, okay, you just flatten it on that, move the datum up again to the upper Ute, flatten it on that, and Spring and Ranch, and flatten on that. And voila, we have the, orientation that we had in the initial slide that was showing if you just map it off the top of the muddy. But what I'm saying here is that we need to rethink the correlations here because it is not a simple filling in a valley. The valley is collapsing into a salt dissolution feature. It is not so much an incision as sands filling in a sag caused by underlying salt dissolution. And it would make sense that the salt could be dissolving because we had an unconformity there at the top of the rosette. And that's what was allowing the fresher waters to percolate down through active faults and get down to the salt and start dissolving it at this period of time. So just talk about using that model, then just how I correlated the sands at Kitty, these the gross intervals. So again, Kitty field was found in 1965. As we said before, it's produced in excess of 23 million barrels. It's still in primary production. And the original oil in place numbers bounce around between a conservative number of 150 to an optimistic number of 250 million barrels, which means the recovery factor in Kitty is somewhere between 9 and 15%. So if we could just get that recovery factor at 35% with some type of flooding, then we could get an additional 30 to 65 million barrels out of this one field alone. So it is a significant target that I think the state is very interested in pursuing. Certainly EORI is. Now, why it's important to study Kitty field, that's obviously it has significant remaining reserves, but many of the problems with Kitty are analogous to what we see in other muddy fields across the state. We cannot inject water from the Fox Hills and the lower members of the muddy, and they just plain, you can't get water into those formations and members. So we need to find a way to inject fluids into this reservoir to enhance production. Also, there's quite a bit of compartmentalization, so that's going to require a lot of very detailed geological mapping in order to properly address how we design our primary and secondary well patterns. This well is in close proximity to the Dry Fork Station, which is just north of this University of Wyoming Powder River Basin 1 well. And so it's a possible CCUS application, which has attracted the state recently. The Denbury Green Corps CO2 pipeline goes right over the field, so there is a potential access to CO2 there if we get to that point that we actually want to put CO2 into this field. And at least there were, and maybe still are numerous CBM wells in the immediate vicinity that could be supplied for gas, for possible gas injection, methane injection into this well, but they're being plugged out as we speak. So at the moment, though, it's still a viable possibility to use those. So again, this is a type log for Kitty Field, just how we break it up into these different members where what's called the Upper Recluse, Cyclone, Lower Ute, Upper Ute, and Spring and Ranch, and then finally the Shell Creek Shales up here. Not all members are present in every well. And for this study, I'm saying that those sands with a gamma ray that are less than 75 API units are considered, air quotes, clean sands. And if they're porous, they would be really good hydrocarbon reservoirs. So this is an isochore of just the Upper Recluse, what's called the Upper Recluse. You see that on the section over there at the right, done by Rondi Martinson et al. Back in '94. And this again has been interpreted to be fluvial channel fill, but as we saw, maybe this isn't fluvial channel fill at all. If you didn't have this model at the right, one could say that that is nothing but a longshore bar, offshore bar series, something like that. It's just shallow marine bar. It's certainly a possibility. And I think we should not be so married to a model that we don't consider other possibilities. Now, if we look at the clean sand portion, meaning again, less than 75 API units on the gamma ray log, it looks like this. Now here, the reservoir is clearly much more segmented, but again, are these things point bars in a fluvial system? Are they estuarine bars? Are they tidal bars? Are they offshore bars? We don't know. And, but I'm not completely convinced that it's fluvial. In fact, I'm seeing more and more arguments that it's not fluvial at all. So I'd be erring toward the side of saying this is probably shallow marine, not fluvial in Kitty anyway. Secondary recovery, if you're going to chase this thing, is going to be optimized by documenting, then flooding each individual pod, if we can find compatible injection fluids, not necessarily unitizing and flooding the whole field in unison. We got to pick each flow unit and flood them individually if we're going to do this thing right. Here's where this interval has been perforated in the wells in this area. And if you look at the clean sand that has better than 15% porosity in it, it's even more segmented. As you see here, this should be the best reservoirs in this particular interval. And again, if you look at the perfed intervals, just for reference sake, so they did a pretty good job of smearing this thing. Most of these, by the way, just as a reference for some people who may not be familiar with Kitty, almost all of these wells are commingled with all of these zones. They've commingled everything, so it's very hard to distinguish what is being contributed for what member. And that presents a little issue, but it's also one of the problems here. You can't just flood one part of the muddy in this field because they're all open in a lot of these wells. Now, this is the isochore of the Cyclone, which is supposed to be an estuarine sand. I don't know about you, but that distribution doesn't look very estuarine to me. And you might notice a little bit of indication here that this is sands appear to be a little bit more prevalent on the north and south sides of the field rather than over the field, which again is another sign that perhaps this isn't really filling in a valley at all. That's actually what you would see if you're expecting sands to be compensating deposition over a bar sequence, for instance, or something. So if we look at the air quotes clean sand in the Cyclone, it looks like this, where again, over the field, it's actually relatively thin compared to around the field. Again, environmental deposition has been previously interpreted to be estuarine. Look at the perfed intervals here, and those are wells that perforated this. We look at the sands that are better than 15% porosity, very, very segmented. And so probably not a lot of communication between these individual pods. And again, just to overlay where the wells were perforated in this interval. So we have quite a challenge to be able to optimize recovery out of this zone, but again, it's quite doable with careful geological mapping. We'll work our way up into the Ute. Now I've combined the upper Ute and lower Ute together here and just calling it Ute. And the reason for that is the Ute is a bit more complicated than I thought it was going to be. So I just lumped them together for the time being. So this is an isochore of the entire Ute section. Again, very, very widespread as far as that goes, but the clean sands within it are oriented like this, kind of a north-northeast, south-southwest orientation overall. Again, rather bar-like, which is what you'd expect. This is supposed to be a shallow marine sand, which it almost certainly is. Again, you notice the segmented nature of these reservoirs. There's not widespread communication across the entire field here. These are the wells that are perforated, mostly on the south end of the field in this interval. If you look at the porous portions of that, again, very, very segmented. So we have, again, a lot of isolated pods to deal with. Again, just showing where the wells are perforated. We look at the Spring and Ranch, and this is, again, just the ice core of the whole section. Very clearly, it looks like a bunch of little sand ridges in a marine setting here. Doesn't produce very well here at Kitty Field. It's very, very dirty sand. Only these portions here have portions that are cleaner than 75 API units. So again, very discontinuous. And these are the few wells that are perforated in that interval. I doubt it's contributing much oil to the system, but nevertheless, they did perforate them in these wells. So one of the interesting offshoots of this is, we need pilot studies, and there's one identified here way back in 2018 when I was working on this initially, and this new work hasn't changed any. So we'll look up here in the Hensley Draw area, which is also called North Kitty. And again, this is just the isocore of the upper recluse sand, where it's cleaner than 75 API units. And you can see again very clearly how isolated these little pods are. Look at a cross section just across here. It is a classic muddy profile where we have the recluse down here and the Cyclone, Spring and Ranch sections. Perfs are down here in the recluse almost exclusively. There's very little contribution probably from this little sliver that sneaked up into the Cyclone, but almost all the production's out of the recluse, which is good because we can now isolate the recluse if we're going to do a pilot study. Below are the figures for cumulative oil, gas, and water out of each of these wells. So if we look at these two pods here and just do some simple volumetrics, if we use the parameters shown up there on the top, just an average porosity of 12%, original oil saturation is 75%, and be pretty aggressive with a B sub O of 1.5. Your oil in place in the northern pods, nearly a little bit over 1.7 million barrels. It's only produced 95,000 barrels. That's only a recovery factor of 5.6%. So again, if you could get that recovery factor up to just 35%, that means you have a remaining recoverable reserves of about over 500,000 barrels. And the southern pod there, again, with over 2.5 million barrels of oil in place, remaining recoverable reserves is nearly 600,000 barrels. So those are nice little pods, which should be fairly well contained. It would be a good place to do a pilot effort if we can find some compatible fluids. So one of the tasks would be to develop a compatible brine that we can inject into that. If we can't do that, could we use some of the coal bed methane from the wells that are all around here and inject that? If we were to inject gas into this, we just did some real simple calculations. We could get much more involved in that, but just to get the ballpark idea, we just wanted to get it up to 1,500 PSI. Our modeling done here by Sritron, one of our reservoir engineers, showed that we would need about a little bit over 400 million cubic feet of gas in the northern one and just under 500 million in the southern one to get the pressures up to 1,500 PSI. Now, that's not necessarily miscible at this point. It's just an idea of what magnitude we're looking at to be able to do a gas flood. That would be moot if we could develop a compatible brine and just inject water into that. Or again, CO2 is always an option. So let's look a little bit beyond the muddy at Kitty just to see what else I'm unraveling as I try to figure this stuff out. So Kitty Field located here, again, the prevailing theory assumes that the flow in these channel systems was from east to west. There are very few significant fields within this channel system. And is that because there's lack of traps because that thing's just running right up dip? Or is there something else to play here? And that, if that is the case, that hypothesis would mean that it suggests there's quite a bit of lateral communication, which is not what we were seeing in Kitty Field. So just something else to question. Now, if you look at the fields here, again, if play back and forth there between that, see where the channels are and where the production fields are located. Again, not a lot of muddy fields going up that channel, a few, but not very significant. So Another interesting point from this map is that none of the fields along this kitty, spotted horse, recluse trend here have been successfully water flooded. Plus, the isochore map doesn't seem to suggest why the fields over here west of Kitty. So something else is at play here, and we haven't answered that. So again, if we look at this here, and I'm going to make a cross section go right up the guts of that valley. Assuming the wheel on my mouse allows me to advance. There we go. So we'll make a cross section, one well in Kitty, just run up to Carson and run right down the guts of that channel with this section and see what it looks like. So here is that section again hung this time on top of the Shell Creek, just to pick a datum. And one question I have is what defines the top of the Muddy? People use different tops for different reasons. There are several flooding surfaces and or bentonites within each of these formations or members that you can use for correlation purposes. Some people have picked the top of a particular stratigraphic marker, whether it's sand or silt, doesn't matter to them. But these picks haven't really been consistent because the character of that flooding surface changes. And so they often drop, and that leads to distorted regional isopac maps. In this section, just for fun, I just picked the colored portion shows the top of the Muddy as defined as the top of the sand where the gamma ray is cleaner than 100 API units. In other words, just cleaner than something that's up in the Maury. Now, if you look at that, a couple of interesting observations. Overall, the Muddy sandstones thin to the northeast, with the upper section getting shalier in that direction. Well, that isn't easily resolved with flow going from the right to the left, going from east to west. Also note that the Skull Creek beds down here are dipping away from the datum line and away from the bottom of the Muddy, which suggests that the basin was dipped downward toward the northeast or north and east prior to much of the Muddy deposition. So there'd be a shallow angular unconformity between the Skull Creek and the beds in the lower Muddy. So such a dip could be used to imply that the flow within this channel system was from southwest to northeast, which is opposite of the prevailing theory. And that presents all sorts of issues, but you could certainly draw that conclusion based on this orientation. Now, if you look at this in another manner here. So here, I've just hung this on a datum, which was my Shell Creek 3 flooding surface, which a lot of people use as the top of the Muddy. And it is the top of the Muddy at Kitty. It coincides with the top of the Muddy. You see as it runs across here how it is up in the Shaley section. But a lot of people use that, including Geodigital, which is that isochore map that I was showing earlier. And that's fine and good. No problem. But note here that it's hard to see on this screen, but hopefully you see it better at home. There's a recluse B and D intervals, a lower recluse. In other words, what I call lower recluse does not equate to what other people call the lower recluse. Seems to be tied to the Skull Creek deposits. They're more parallel to that than to the upper units here. And the recluse A section, what I'm calling recluse A, could therefore be a transgressive sand that unlapped onto this now tilted basin that was dipping toward the north and east as the sea returned to this region sometime later. Meaning again that there would be an unconformity of some duration between these two recluse intervals. So if we hang it down here on the Skull Creek 7 again, and just look at that here, see how flat this top of the recluse BD intervals are. And notice how what's called the recluse A or upper recluse by a lot of people's terminology climbs in the section going this way. So, that again seems to be indicating that, again, if you accept that up dip maybe was to the left in this section, back in this time, there's an apparent onlapping nature of the beds younger than this recluse B and D interval. And so the recluse A section, as I was postulating before, could therefore be a transgressive sand that onlapped onto the now tilted basin that was dipping toward the north and northeast as the sea returned into this region sometime later, meaning there'd be a major unconformity between those two intervals. So perhaps what I'm calling recluse A and other people call the upper recluse generally shouldn't really be called recluse. It is really a completely different family in a different sequence than what I'm calling the recluse B and D sections. Now, in this section too, the anomaly thick areas, just to remember, are, I think, postulated to be, for me anyway, that these are caused by dissolution of the Permian pine salts. So we can see these abnormally thick sections going up here, and that's because we're still having the effects of the salt dissolution under us, which again is complicating our correlations. We need to be pay attention to that as we correlate these things. If you do a cross section just running across this major valley, just to see what that looks like. Now here, again, looking at these Skull Creek data, see these horizons coming over. This is truncated. So that is a scour into the underlying Skull Creek. Again, the dark blue here would be the Recluse B and D sections. This would be what I'm calling Recluse A, Cyclone, U, Spring and Ranch. And again, datum right now is top of the Shell Creek. And pretty nice configuration. This fits the classic model of a muddy. But of some interest here is notice how this thing is deepest here and kind of slides this way. Also, notice how the muddy beds are thinner here than over here, suggesting perhaps this way, which is north, was a little bit down dip at this time. And here, if we hang it on the my favorite Skull Creek marker, it looks like the scour here is about 25 feet. If we remove the distortions from all the overlying beds and salt dissolution. So again, the anomalous thick areas, I think, are due to the salt dissolving underneath us here pretty much during cyclone and Ute time is when that apparently was happening, because that's where most of the thickness changes occur in those intervals. Now, there are a few additional studies we've done that we're trying to plug into this. And again, we need to do a lot more studies. It's hard to do that with the skeleton staff we have. So we'll get to hopefully working jointly with you guys in a little bit here. But we have published these two field studies over here. We're working on this one right here. And we'll look at these and just for correlation purposes, jump correlations from Kitty Field over to these fields to see how they fit into the picture. So look at this Hirsch area first, that was the northern one here. And you can see, again, line of section is running from Kitty up here to this well in the Hirsch study area. The Hirsch area is comprising Cyclone and Ute. Spring and Ranch is shaly here. Again, a lot of people would pick that as the top of the muddy, even though it's just as silty as is the Mowry above it. And Ute is well formed. The Cyclone's pretty well formed. There is no recluse in this area at all. Now, this is an interesting area. The Hirsch area was found with 3D seismic. The operator up there shot 3D seismic in 2018, subsequently drilled 3 successful Wildcat wells, all 3 produced. And it's drilled a successful offset to one of those just this last year. And we did receive a core from those guys on that well, which is good because we are certainly lacking in core. We'll now look at the Rosette and Windmill fields that were kind of east-southeast of Kitty there. Again, this is from this publication here. You can look that up online if you want to. And this is how that correlates. Again, Kitty Field here running over through this well over to the Windmill field here. So again, all we have here are Ute and Spring and Ranch. Now keep in mind the Rosette field was originally the type locality of the Rosette member, but there is no Rosette, it's Ute, which tells us how problematic we've been in the trying to figure out what's going on in the muddy section for a great many years. Now, finally, we look at the Skull Creek correlation here. So just jumping way down from Kitty all the way down here, had to come up here just north of the study area just to get a really good log that went a little bit deeper. And again, Kitty Field here, running up here into the Skull Creek area here, it appears to be mostly equivalent to the Ute, Spring and Ranch intervals here with an unconformity right there. So, you know, these correlations down here are not mine, so I can't vouch for them right now. But point being, though, that I think, again, the muddy section here is the upper muddy in that area. So probably that entire channel trend is we're dealing with the upper muddy equivalents, what we see at Kitty Field. So I'll just present a really wild and crazy theory for muddy deposition here. I mean, this is really preliminary. And it's really mostly for fun, just to get some people thinking. And this whole talk is really meant to inspire people to have some conversations and maybe get to rethink about what's going on in the muddy and maybe generate some collaborative work with a lot of you folks so we can try and get this thing figured out. So again, looking at this same map here, just that we have the spotted horse kitty trend where you couldn't water flood any of that. These recluse members in these fields do not match very well with what's called the recluse, much of the recluse in this channel system, which is interesting. And so combining the findings of this brief regional look and the little field studies we've done before, what if this is a situation? The rosette is really an upper shore face, strand plane sand, and it was exposed, which is why we have kaolinite there. And then just down dip from that, and what I'll just call lower shore face here, is what these sands are in the kitty recluse, spotted horse trend. And they're just reworked rosette sands that are a little bit higher energy and cleaned up. And as the seas continue to withdraw, we start getting that channel incision down there. It is in the northeast there of those areas. And an offshore bar trend again was forming, as I was saying, the retreating sea resulted in channels forming that, what I'm calling a deltaic system, developed in the northern Powder River Basin with a major unconformity on top of those lower recluse sands and on the rosette. And that lasted for a while. The basin got tilted, and then the returning muddy sea during what has been called upper recluse time then starts inundating that channel system. Now, because of that unconformity, episodic dissolution of the pine herbaceous salt underneath this begins, creating sags that are further complicating our correlations and increasing local accommodation space for a lot of the muddy deposition. And continued salt dissolution and sea level rise during cyclone time resulted in shallow marine and local estuarine and tidal bar deposits, as significant shales occurring on top of the cyclone, which might represent another intra-muddy unconformity, or at least a still stand. Now, at the same time, channels began to form in the Newcastle portion, the southern portion of the basin, during early Ute time, top of cyclone time. And again, perhaps because of that sea level drop, I'm postulating at the top of cyclone, which would make sense. And so we're getting channels formed there, but the channels are being infilled there by Ute equivalent sands, which present the same problems because they're getting, again, reworked clays in there that present in the lower sands and present problems in production. So as sea levels continue to rise during Ute time, then offshore bars are formed throughout the Powder River Basin and even in the paleo high areas of the basin, which is why we have Rosette and Hirsch fields forming over here on this paleo high finally. And that's why those are only in the upper portions of the muddy. And continued sea level rise results in what we're calling the upper Ute and the spring and ranch deposition, and even in the shallow areas all across, everything's inundated now. And finally is capped by the Shallow Creek and then the Maury. And just to show that isn't totally off base, this is just a picture again. Picture that if that's a delta system, here is the present day delta of the Lena River over in Russia. And you see how these distributaries run out into the sea like that. So kind of interesting. Again, just something to think about. So the offshoot of all this is that I think even if I'm close to correct on some of this new thinking, members of the muddy have been miscorrelated, and the EOR efforts, I think, have been incorrectly designed in the past because we haven't been paying attention to the salt dissolution issue. And we have a model for the muddy, which isn't universally applicable. I think it is applicable in part of the muddy, but it is not everywhere applicable. And we're trying to force the correlations to fit that model. Detailed and accurate reservoir characterization is the key to any successful efforts to improve recovery. And so that's particularly true in the muddy. And we have to start rethinking how we correlate. So due to these miscorrelations, I think it's possible that wells have been placed, improperly, even for primary recovery efforts, let alone secondary. And compartmentalization is a significant issue, which again goes back to careful geological mapping. We really need to pay attention to how we're correlating this stuff. Another point, I think, is what's been called the upper recluse member within the kitty recluse spotted horse trend is probably different and may have different properties than what's called the upper recluse in the apparent channel deposits. And I think for reasons we kind of touched on. Different members of the muddy may require different methods to optimize hydrocarbon recovery. We certainly know that in what we're calling the recluse members. The upper muddy floods much better than the lower muddy, mostly because we think of the clay content. And that again goes back to the mineralogical contents of these different members may be different. So we have to pay attention to that if we're going to design optimal injection fluids. So if this new theory regarding, the salt dissolution is valid, which I think it is, it really could result in a not only improved EOR efforts, but might also lead to improved exploration, because now we can start predicting where we can find channels by even perhaps using seismic to find some of these salt dissolution features. And general estimations at this time suggest that there's at least 100 million barrels of additional production we can get from existing muddy fields. So again, this is a very, very important target for Wyoming. So what I've wanted to do for a while, and we want to do now, I think wholeheartedly, is form a muddy consortium. And we're going to continue to work on Kitty Field and additional regional work, but we'd like to develop this consortium with muddy operators, and we can use Kitty Field as one of the templates for our studies. But we want to do really good reservoir characterization and mapping. We need to obtain core from each member of the muddy. That could be from one well, but we need fresh core. We are very lacking in core. And maybe EORI can help with some of that, paying for some of the coring, maybe the analysis, something, we'll be talking about that. We need to obtain representative samples of in situ formation water from each member of the muddy, and the operators can provide that. We only need a pint of it to analyze it. It's not like we need gallons and gallons of water, but we need to analyze what the in situ fluids are like, because by definition, those are compatible to the reservoir. We also need to obtain nearby samples of water from the Fox Hills Formation. Again, operators can provide that without a problem. And we like to conduct a brine compatibility study, preferably using Puri labs, but we don't have to use them, but we prefer to use them. We'd like to conduct core flood experiments to determine the type of formation damage caused by injecting Fox Hills. And we'd like to create a synthetic brine that matches the produced brine that we can analyze, and then use that to inject and see if we can prevent any formation damage. Then we'd like to find the most economical way to create a synthetic brine, and then use that, figure out what's going to cost on a large scale and use that to conduct a pilot study. And if that works, then we're off to the races. We can start putting that in all these fields all across the state, or at least have a template for doing that. We'd like to also develop a model and run simulations to determine the most effective EOR design for Kitty Field and any other field we'd be studying. Again, using whatever fluid we want to put in there, synthetic brine, CO2, something else, gas, whatever people want, but it would be good to do that. And then we'd ultimately make recommendations to operators to implement field-wide floods at Kitty and elsewhere. And again, we'd be probably picking on how to flood individual flow units, not the entire field at once. It is not feasible to do a whole field flood at a place like Kitty, and probably many of these other muddy fields. We're going to like to conduct regional correlations and mapping of the muddy Newcastle, and then provide the interpretations to the group and what the heck these maps mean. Just having a map is great, but what inferences, implications can we get from those maps? I'd like to conduct some regional correlations of that Pine and Hervey salt and basically improve that map that was published in 1981 and see what else we can learn from that. Determine to what degree that the salt dissolution is affecting these muddy fields. And again, is it possible to obtain some seismic data? A lot of it's available for virtually nothing right now. They're going to help us define some of that salt dissolutioning where we don't have good well control. I'd like to determine recovery factors in several of these muddy fields under primary and secondary production, and see if there are any patterns in these recovery factors. I mean, do certain beds have better recovery factors than others? Do certain areas have better recovery factors than others? Do certain well patterns have better recovery factors than others? And so we can infer reasons for these differences and then spread that off to the group too, and then obviously determine other candidates for field studies. So that kind of wraps up that, and I'm hoping that encourages a bunch of questions, thoughts, comments, not just necessarily now, but even in the future. For those who are too bashful to ask now, we have a question session at the end of this here that people can do online or here, obviously. But you can contact me here at this contact info anytime. I'd be eager to talk to anybody about this. You can come up to my office, go through maps, whatever you want. I think this is a very important topic and one that we should all be pursuing. So anybody got any thoughts, questions? Didn't notice anybody completely fall asleep, so that's always a good sign. Clues you. Yes, I may have an answer.
the additional recovery from the kitty or muddy,
Yeah, the muddy, yeah.
would that be from secondary or additional recovery methods, or would that be new oil?
That's new oil using secondary recovery. That's a good question. That is not doing like CO2. That's just assuming we could get up to 35% recovery factor. We could get that additional recovery up to 65 million barrels if we use a 250 million barrel original oil in place number. That's
Okay.
the upside.
So that's just with the oil that we know that's already in place.
Right, right.
What are the existing operators in Kitty Field doing? A part of this study or?
Well, that's a very good question. We have had very good interest expressed to us from Contango, which is one of the major players in Kitty at the moment. We haven't yet talked to Kennedy, who's one of the other major players. We hope you join. But we are getting some very positive feedback from the few people we've talked to. We're kind of making initial approaches to see what the interest is, and there is interest there. So we think we're going to pursue this.
How are you gonna get the regulators on board, not to form the whole Kitty Field with the unit? Are you talking about trying to form a section, half a section unit or?
Well, it's another excellent question. We need to talk to the Oil and Gas Commission folks and get them to understand what we're trying to do and hopefully win them over. That's not a guarantee, but I think, the head of the Oil and Gas Commission now, Tom Kobach, he's a pretty reasonable guy. And we haven't yet presented this to him, but that is in the stages right now of getting done. And we hope to, when they first saw the embryonic parts of this, they seemed kind of receptive to, oh yeah, we understand why you wouldn't want to flood the whole field at once. So at least the thinking is there. And if we can get the execution done, then we're home free.
I think your bigger problem's gonna be the BLM.
Yes, we have to talk to them too. You are right. BLM is always a problem, particularly right now. But we have to talk to them too, because I think overall, even the BLM, I think ultimately wants production. And if they do, the best way to do that is to single out these flow units and flood them individually, not try and unitize an entire field with multiple flow units that don't relate to one another. And again, that's going to come down to, we have to show that it's possible to map these things properly to convince them that, yeah, I believe in your map. You can't just arm wave it. You have to say, yeah, this thing's isolated from that. There's no reason to form a unit. These two guys don't talk to each other. And hopefully, probably that's going to require ultimately getting a little bit more data. We're going to need pressure test, trace it or something to totally 100% convince them of that lack of communication. But I think the evidence is there on the logs even. They do not look like they're continuous reservoirs. I think the production shows that. Since there's no injection there yet, you can't prove conclusively that this doesn't talk to that because we don't have any injection fluid going in there. But I think the weight of the evidence right now would be, I think, helping convince them that we got to go down this path. What they ask in addition to the geology, that we have on the subsurface will be a big question. That, again, that's a wild card right now. But we have to go down this path because I don't think you're going to unitize the whole field adequately to get this done right. But if that's the only game in town, we'll find a way around it. We'll unitize the whole field and still flood pods at a time, and we'll figure a way to do it. Yes.
Yeah, I believe in segment this thing. When I was in the geology that I did 25 years ago. At that time, I suggested, I think, 7 different pods that could be worked on separately. And I think I can convince the Oil and Gas Commission. I think I probably convinced the feds that it has to be broken out. I just don't see that as a problem.
Yeah, I tend to agree with you. I mean, I'm always surprised, but logically, I think that is the case. I think we can make a strong case for this and get them to agree that we need to segment this thing out to do this right. And it's going to be the same situation in other fields. It's not just Kitty. We have other muddy fields that have similar problems. So this will be a template for what we do elsewhere too.
I have an online question from Vello. I'm just going to allow them to talk.
Sure.
Vello, go ahead.
Yes, do you have information on the, let's say, the characteristics of the water that's in these various formations? For example, in the Recluse, in the Ute, etc. It's mineralogy, and I'm just assuming that the formation water is compatible with the clays. I mean, that may not be the case, but if it is, then that could be a lead towards what you might be looking for synthetic fluids to flood the muddy.
And that's a good point. That is exactly the plan. We do not have those analyses at the moment. We are asking operators to provide them. Many of these wells produce very, very little water, so they're hesitant to go out there day after day after day after day after day to get a thimble full of water so they finally get enough water to analyze. But I think we can convince them to do that. But we proposed that a few years ago and it was met with a resounding thud, but I think we can convince them that this is a necessary step now. And again, that's the reason to form this consortium. I think we'll have people that are all thinking on the same plane finally, and we can get that cooperation. And you're dead right. I think that it is likely that the in situ fluids are compatible with the formation. And all we need to do is copy that in situ fluid using the Fox Hills and make a synthetic brine. That was the whole reason for doing these brine studies and core floods, is use that synthetic brine to flood the core that we get and see if it doesn't cause any damage. And if it doesn't, hallelujah, we got an answer. It's just a matter of how much does it cost to make that synthetic brine? What's the cheapest way we can do it? We'll probably talk more about that tomorrow, or Thursday, I guess, huh?
Thursday, yeah, look forward to it.
Me too. Any other questions? And again, those who are too bashful ask now, or if you're like me, you think of it about 2 o'clock in the morning. You know, that's my contact info. My office door is always open. Just come by, call me up, email me, anything you want. I'm be tickled to death to talk about it and to share ideas and concepts. So.
Another question.
Yes.
If there's an operator on geology, they kind of come to this consultant, what they can be the contribution?
Well, that will have to be worked out, but obviously be in kind. I mean, if we're working with Peer Labs, it's going to take money. And EORI can contribute some of that, but we're going to have some operator contribution if we're going to get the proper core flood work done. I'm not talking about huge chunks of money, but the more members we have, the less money it is per member to get that done. And we'll have to work out what the consortium members get out of that. Obviously, they get the information, but it's, you know, if it's proprietary, so it's exclusive to them for a period of time. So they learn by contributing to the consortium, they learn all this stuff that nobody else knows about for a significant period of time before we publish on it. That might be enticement to join the consortium, because now you'll have a leg up on everybody else, providing you're in the consortium. Yes, sir.
Just 2 things about fluid compatibilities, etc. Wayne and I were involved with the flood at North Carson, and it was partially successful. It was all in what we call nuclear sand. And we determined that nobody had done a nuclear sand flood that was successful at that point. The question was, why not? And we looked at the fields that we looked at in this area. They all of them had problems with injection. When they would inject, their pressures would go up. Sometimes within 30 days, they were already
Frac pressure, yeah.
frac rate. So it looked like, well, you gotta have a more compatible, you know, to get water in. And we kept looking around, and the Whitaker field, which is just north of my car, is still in the plan that everybody saw just now. There was 2 wells that responded to flooding early on in that Whitaker field. And those 2 responded to actually injection of wastewater in an offsetting well from the dip side in the water lane.
So they were in re-injecting produced recluse water?
Well, Fred Odico was one who was doing it, because it was pretty sharp guy. But he was using, he said to me, he told me he was using both muddy and Melaleuca
Okay,
water to inject into that well program. He was getting paid to get rid of the water.
Sure.
That's all. Then the two offset wells responded, obviously got their production. The rest of the field was the water flooded, that did not respond at all.
because they were using Fox Hills water. The rest of the field, yeah. So yeah, when you told me that story, that was again, I think reinforcement that we need to just get compatible brands. It'll work. Just we can't use Fox Hills water by itself. It's got to be treated somehow. We got to mimic what's in the formation already in order to get this thing to work.
Yeah, and number two, when we did flood, we were able to get water into the formation. And we had a down dip water lake, by the way. By the time you go north, you got a lot more water. The south end, you don't have water. The north end, you have lots of water. But so we were in the down dip water lake, and we were injecting in that water lake, use potassium hydroxide treatment on those injection wells, we were able to get water into the ground. But on the water, which did initially increase oil production considerably, once the breakthrough occurred with the water, we were done because it caused the wells essentially to become fluid.
Why do you think that is? You think it got so diluted by that point that it clogged things up near your producing borehole? Or do you think there's something else at play?
I always suspected it was moving fines, but I don't know.
Another reason to do the core flood work, we need to know what's really going on down there, you know, when we start putting this stuff in. Are we just moving fines around? We're still going to have problems, or does it actually solve the problem? You know, potassium hydroxide, depending what concentration you used, may have been a partial solution, but not the total solution. We don't know. It'd be, but that you were on the right track, obviously.
We increased the area where we're trying to go.
Mhm.
Sure.
Yeah.
By the time that water got to the
Yeah.
Calcium carbon, calcium chloride water. They use calcium chloride to stabilize clay.
Mhm.
Their whole system. The pipeline, and I talked to the engineer that did that. The pipelines, everything ended up filled with scale,
Carbonate scale.
calcium
Yeah.
carbonate.
Yeah.
So
Around the whole lines, everything
Yeah.
is reduced down to zero, couldn't get it down to 5 points.
yeah, they can use water to buy.
Yeah.
For the first party, you said there's some checking and some will don't have any response. Is that we are in the same part or separate part? You checking and is there checking and there several couple wells, no response checking. Is it we are in the same part or separate?
Same compartment
What's that?
with it. Same compartment, you know, so you were in the same sand segment. You were.
Yeah, because we got a good response initially. We got a great increase in oil production in short order. It only took about, as I recall, about 30 to 60 days to get that response. And we continued to have that response for, I don't know, maybe 6 months total. And then the water got to the producing well and it just basically shut off.
talking about this first part, you say, you take it here, there's a proposal well, right out. Some will suppose that it respond, but not.
They had a good response, I think, from,
And we had a good
Yeah.
response.
You need to,
And it was right here in the Gulf War, it's kind of wonderful.
yeah, I read the paper, right?
well, thank you all for coming. Appreciate it. And again, as I said, if you guys got any thoughts, comments, want to work together, whatever, give me a holler. And help yourself to the rest of the donuts.
Like you say, good job.
Oh, you're welcome. Thank you. Kind words are always appreciated. I'll pay you after everybody leaves.
For the donut?
Yeah.
All the donuts.
Yes,